Okay, the next thing we're looking at in trig is something called addition formulae. Now, addition formulae is a collective name given to 4 formulas that you'll learn involving sine and cos that we describe as something called a compound angle formula. Okay, so we've got the first one is sine A plus B. Now, sine A plus B can be written as sine A times cos B plus cos A times sine B. Okay, now as we can see, it's sine A times cos B and cos A times sine B with a plus in the middle. So these are beside each other here, which implies that they're multiplying at that point. Okay, now this is given to you in your formula sheet. Okay, so it's not compulsory that you remember that, because you will be given it to you in any assessment in the formula sheet. Sine A plus B is equal to sine A cos B plus cos A sine B. That's the first one. We've got another 3 to go. We're going to concentrate on 2 just now. That's the first one, and here is the second, also given to you in the formula sheet. Sine A minus B is sine A times cos B minus cos A times sine B. Now, in terms of where do these come from and the justification as to why these are true, that's something that you can look into. It's at the front of chapter 11 in the addition formula. There's proofs to show you how you get from here to here and get from here to here, but that's not something that you need to concentrate on in terms of answering questions in the exam, and I'm not going to spend time on it just now. Okay, so let's just highlight these. Those are 2 important facts and 2 important results. Those are true, and we're going to use them to solve certain problems today. Okay, so let's put this into practice and see what could be asked of us. Example 1. Let's say in example 1, right, let's start nice and easy. We're going to write down a formula for sine P plus Q. Okay, we've got stand-ins here, we've got substitutes, which is A is now P and B is now Q, so that's really straightforward. If I was wanting to expand that out then, so it's going to be, well, sine P this time, and cos Q plus cos P sine Q. Right, dead straightforward. Okay, that's that one. Okay, let's try something that's going to just examine this a wee bit more. Example 2, and example 2, let's go for this time. We're going to expand out sine 90 plus y. Okay, so look at the pattern here, P, Q, PQ, right? So that's going to be sine 90 times cos y plus cos 90 times sine y. Now, a common mistake not to make is sometimes you'll get folk putting in a plus in here and a plus in here. The plus is in the middle. Here and here, that's a multiplication. Okay, so we've got sine 90 cos y plus cos 90 sine y. Now we can go further than that using our exact values. Now, if you go to your table, your table of 15 exact values, that will tell you that sine 90 is equal to 1, and it'll also tell you that cos 90 is equal to 0. So what we've got then is 1 times cos y plus, well, that's 0 times sine y. Okay, 1 times cos y then is just cos y, and 0 times sine y is just 0, so the final answer then is just cos y. Okay, still dead straightforward, and let's try something else then. Okay, so let's go for an example 3. An example 3 this time is, let's expand out sine 2 pi minus theta. Okay, so that will be sine 2 pi cos theta minus cos 2 pi sine theta. Okay, so what was 2 pi again? That's equivalent to 360 degrees. Now if I think about my sine curve, okay, y equals sine x, at 360 degrees at 2 pi, it holds a value of 0, okay? And if I then think about the curve for cos x, okay, at 2 pi, this time that holds a value of 1. Okay, so sine 2 pi then is equal to 0 and cos 2 pi is equal to 1. Okay, so that's 0 times cos theta minus 1 times sine theta. 0 times cos theta is 0, minus 1 times sine theta is minus sine theta. Final answer. Okay, so let's try another couple of things that might be asked of me then. Let's try example 3. I'm going to find the exact value of sine 75. A query could come up at that point, which is that the exact values are 0, 30, 45, 60, 90, and it could be queried that you've never been given an exact value with the number 75, which is true. The table exact values that you've been given, there's 15 of them, and it's sine, cos and tan for 0, 30, 45, 60 and 90. What I would say though is we could combine some of these numbers together. Could we combine the 45 and the 30 and write sine 75 then as sine 45 plus 30? Now that's a true statement because sine 45 plus 30, well 45 plus 30 is 75, so that's the same as sine 75. I could now use that formula. And let me just remind you of that again. Sine A plus B equals sine A cos B plus cos A sine B. Okay, so that would then be sine 45 cos 30 plus cos 45 sine 30. And at that point, I can now go back to my 15 exact values that I know. With sine 45, that is 1 over root 2. I'm then multiplying that by cos 30. What's cos 30? Again, go back to your table exact values, and cos 30 is root 3 over 2. What about cos 45? That's 1 over root 2. And what about sine 30? That is 1/2. Okay, so now I'm thinking about a simple National 5 work, which is what? That's multiplying fractions. How do you multiply fractions? You multiply top and bottom. So 1 times root 3 is root 3. Root 2 times 2 is, we'll just put them together, 2 root 2. 1 times 1 is 1. And root 2 times 2 is 2 root 2. Okay, so I've got root 3 over 2 root 2 plus 1 over 2 root 2, so I just combine them together. Not much to that, that's just root 3 plus 1 all over 2 root 2, final answer. Okay, let's try another. What about finding the exact value of sine 15? Well, again, 15 is not one that you were given. You were given sine, cos and tan for 0, 30, 45, 60 and 90, but if you ever think about it, is there anything we could extract from here? Could we use the 45 and the 30 and make that sine 45 minus 30, which would then be sine 45 cos 30 minus cos 45 sine 30. That's quite simple, and that's true because 45 take away 30 is definitely 15. So sine 15 can be written as sine 45 minus 30. Okay, so sine 45, 1 over root 2 multiplied by cos 30, root 3 over 2 minus cos 45, 1 over root 2 multiplied by sine 30, which is 1/2. Okay, follow the pattern of last time. 1 times root 3, root 2 times 2 to root 2. 1 times 1 is 1, root 2 times 2 is 2 root 2. Put them together. Root 3 minus 1 over 2 root 2, final answer. Okay, so a lot of this stuff is like just performing wee tricks to try and prove things are true and write things in different ways using those two formulas. Sine A plus B equals sine A cos B plus cos B sine A, and sine A minus B is equal to sine A cos B minus cos A sine B. Okay, let's try another one. Right, this time let's go for, we're going to try and prove, that sine theta plus pi over 6 can be written as 1/2 bracket cos theta plus root 3 sine theta. That may look as if it's quite challenging to do, but what I would recommend that we do is just take one step at a time and follow what we know. Okay, so what I'm expected to do then, expand that out. If it was one point that I would make is try not to fall into a trap here, which is to think that that can be written as sine theta plus sine pi over 6. That is not a result. It is not true. You must use your expansion. So, just quick reminder, what's your expansion? Sine A plus B is equal to sine A cos B plus cos A sine B. Okay, so in this context then it's sine theta cos pi over 6 plus cos theta sine pi over 6. Okay, so we're radians here, right? Let's base again, right? So from previous videos, pi radians is 180 degrees, which means what? That means that, well, if pi radians is 180 degrees, then pi over 6 would be 180 divided by 6, that's 30. So in essence what we've got there is cos 30 and sine 30. Right? You're probably writing in radians but thinking in degrees, which is fine, but if it's a radians question, let's keep writing it in radians, but you know, internally you're thinking probably in degrees. Okay, now do we have exact values for cos 30 and sine 30? Yeah, we do. Root 3 over 2 and 1/2, and that's from a table of 15 exact values. So I've now got sine theta multiplied by cos pi over 6. Cos pi over 6 is cos 30, that's root 3 over 2. I've then got, well that's a mistake there, that should be cos theta. Okay, so I've then got cos theta multiplied by sine pi over 6, that's sine 30, that's 1/2. Okay, so I've now got root 3 over 2 is sine theta plus 1/2 cos theta. Okay, the question says prove that that can be written as that. Now, that question is telling me to take out a factor of 1/2 and open up a bracket, right? It's actually guiding me to do so, so that's what I'm going to do. I'm going to take out that common factor of 1/2. So 1/2 multiplied by what gives me root 3 over 2, so that's going to be the root 3 sine theta. And 1/2 times what gives me 1/2 cos theta, well that will be my cos theta, and that's the result that I was looking for. Okay, let's try something else. Okay, this time we're going to involve some right angled triangles in the mix here. Now what I'm going to say then is that we've got a right angled triangle that looks like this. Okay, Okay, that's 4, that's 5, and I'm going to say that that is the angle B. That is a right angle triangle. And we've got a second right angle triangle, which looks like this. I'm going to say that that is the angle A, that's 5, and that's 13, and there's my right angle. Okay. Now the question then is, show that sine A plus B is equal to 56 over 65. Okay, right. Now let's just unpack this question. See how are we going to get to that result and what does that even mean? Okay, well the first thing that I would do is start looking up at these right angle triangles. Now what's the first thing that I could do here? Well, using Pythagoras I could find the third side. So I'm going to do that here. Okay, I'm going to call that, just now I'm going to call that T. Now using Pythagoras, that's a shorter side. I'm going to do subtraction, so that's going to be T squared equals 5 squared minus 4 squared. T squared is equal to 25 take away 16. T squared equals 9, and T would be equal to 3. Okay. Now up here I'm going to call that Q. It's a shorter side again, so Pythagoras again. Q squared equals 13 squared minus 5 squared. Q squared equals 169 minus 25. Q squared equals 144, and the square root of 144 is 12, so Q is equal to 12. Let me just put that in a different colour pen so that it's dead clear. Okay, so I've now got 3 lengths of the triangle 13, 12 and 5 and 5, 4 and 3. Okay, show that sine A plus B equals 56 over 65. Well, first of all, what is sine A plus B when I open it up? Using that formula that I've just learned, it's sine A cos B plus cos A sine B. Okay. What's sine A? That's my first task. Find out what sine A is. Okay, I'm going to go up to the side and see if I can work that out. Now this isn't anything new to you. Okay, so sine A, that's going to be the opposite over the hypotenuse. Thinking about SOHCAHTOA. Okay, sine is opposite over hypotenuse. So just look at how I'm highlighting this. Sine A equals the opposite over the hypotenuse. That is 12 over 13. Okay, what about cos B? So let me just tick that one off. I've got that one. Let's go after cos B. Okay, cos B. So SOHCAHTOA. So SOHCAH, cos is adjacent over hypotenuse. So it's the adjacent over the hypotenuse. Well, let's go to the triangle with B this time. Okay, we're at the triangle with A, now go to the triangle with B. Adjacent over hypotenuse. Adjacent over hypotenuse. 3 over 5. Okay, got that one. Next one, cos A. Back to the triangle with A. Okay, so cos A, adjacent over hypotenuse, 5 over 13. Okay, I've got that one. Final one, sine B, back to the triangle with B. Okay, so sine B then is opposite over hypotenuse, 4 over 5. Okay, now what I'm going to do is substitute those 4 things in. So the first one then is sine A, where's sine A? Up there, 12 over 13. Multiplied by cos B, where's cos B? 3 over 5, plus cos A. Okay, I'm now on cos A. Where's cos A? 5 over 13 multiplied by sine B. Where's sine B? Up there. 4 over 5. And this was all just from a bit of Pythagoras and a wee bit of SOHCAHTOA. And knowing that that's my expansion. Okay, multiply top, multiply bottom. 12 times 3 is 36. 13 times 5 is 65. 5 fours are 20. 13 times 5 is 65. 36 over 65 plus 20 over 65 is 56 over 65. And there we go. That was the result I was looking for.